We are discussing about range image analysis. In the last lecture, we discussed different mechanisms for sensing range images. In this lecture, we will be discussing different concepts of differential geometry, which will be useful in processing range data. So, let me first explain how parametric curves in 2D they are represented mathematically. As you can see here that here you consider a particular parametric parameter which is a subset of the real space whose values lie in an interval of real space, and you are mapping this parameter this parameter value to a coordinate of a two-dimensional space. So, that is why it is a mapping from R to R square, and in parametric form we can represent this parameter say t, which is a variable which takes values from an interval of real space. For example, from interval between 0 to 1 the parameter values may vary, and for each parameter value you get a coordinate within that within that interval you get a two-dimensional coordinate, which is denoted here as x t as the point, and its x coordinate as u t is a function of that parameter, and v t that is the y coordinate, which is also a function of this parameter. So, this is a parametric description, a very simple way to describe a curve as a set of points, and it is a continuous curve if the parameter varies continuously and these functions are also continuous over t. So, this curve also a continuous curve can be represented in this fashion. Now, when you compute a tangent, because of the continuity you can compute the derivatives at those points. If it is continuous of at least of order 1, it could be continuous of order 2 also or higher orders. So, at least when it is continuous of continuous curve of order 1, then you can compute the tangent, and which means mathematically you can very easily get this tangent information by the tangents at those locations are also denoted by the corresponding derivatives of those parametric curves, which is giving you the tangent information. It is giving the vector actually, it is giving the directions of the vector with respect to that point. And you can also compute the curvature at that point by performing these computations. What you need to do, you need to compute the first derivative and second derivative of the parametric curve, and then perform these operations. You can see that numerator is nothing but the determinant of this quantity derived from first derivative and second derivative of the parametric curves, which is shown here as a determinant value, that is in this case you can see that this delta u delta t and delta v delta t that is giving you the corresponding value. So, given a particular value of t, you can get a scalar value here, all the scalar values are obtained, and then you perform the determinant of this matrix, and this is the magnitude of the tangent vector. So, if your tangent vector is u prime t and v prime t, that is shown here. So, this magnitude should be u prime t whole square plus v prime t whole square and square root. Let me write it clearly here. So, u prime t whole square plus v prime t whole square, that is the magnitude of x prime. And when you are performing, when you are raising it to the power 3 or cube of this amount. So, this is the quantity you are measuring. So, this is how the curvature could be computed at any parameter value. So, that is just simply explaining that part. Now, let me consider the parametric representation, curve representation in 3 dimension. So, like 2 dimension, you can see it is all these notations are simply extended in this particular context, where the parametric curve representation is a mapping from a 1 dimensional real space to a 3 dimensional real space. So, again the parameter values varies within an interval of real space I, and you have an additional coordinate that in the z, which has been shown as a function of w t here, in addition to u and v functions for corresponding x and y coordinates. Similarly, the tangent which is computed in 2D by taking the derivatives of respective functions, that also you do it here, and for curvatures also you see that the expression remains the same, only its interpretation is bit different. You have the cross product of the vectors x prime and x double prime. So, this is cross product of 3 vectors. You take the double derivatives, which means in this case you are taking u prime t, v prime t and w prime t. So, that is a vector notation. So, I am using column vector notations. In this lecture slide, everything is shown as row vector, but throughout I have used column vector notation. So, you should consider in some cases I will be using column vector notations for doing the exercises. So, let us consider this is this vector, this is what is x prime t, and x double prime t is given as the double derivative of these functions. So, u double prime t, v double prime t and w double prime t. So, given a value of t, you can get these 3 vectors and then you perform the cross product. That is the interpretations. And similarly, x prime q magnitude we have shown in the 2 dimensional case, you have to extend that concept of this vector. So, take the magnitude of this vector and raise it to the power 3, that would give you the denominator. That is how this curvature is computed. So, now we will be discussing about the parametric curve which is lying on a surface. So, in the previous case we have considered any parametric curve, but with respect to surface let us discuss. As such, if I look at the curve in an independent fashion, our previous analysis or previous representations all are valid. We represent it as a parametric curve representation of 3 functions of parameters for x, y, z coordinate given as u t, v t, w t. Similarly, its tangents are given by their first derivatives and curvatures are computed at every point by computing the cross product of these 2 term x prime, x double prime, taking the cross product and the magnitude of the cross product. So, that I missed in the previous slide. So, actually it is after computing cross product you have to take the magnitude of the cross product, and then in the denominator you compute the tangent by taking the first derivative and take its magnitude and raise it to power 3. So, if I divide these 2 terms I will get the curvature. So, that is what we discussed. So, now let us see with respect to surface what other kinds of concepts are there. Consider a point at a particular point of a curve and consider the tangent directions. So, this is the tangent directions at that point, say, which is given by t t in our notation, and consider a very near about point, say this is the point which is very close, infinitesimally close point on the curve. So, this tangent and this curve, this point will form a plane and this is this plane. Okay. So, it is a kind of plane where the tangent is lying, also the curve is lying. So, it is a tangential plane kind of thing, and which is called actually osculating plane. We will see the concepts, names, nomenclatures later on. First, let me define these concepts first. So, in that plane where the tangent is lying and also curve is lying, at that particular point, you can define the normal which is lying on that plane. So, normal which is perpendicular to this tangent and which is lying on that plane. So, this is the normal of the curve. So, this point is P and this is the tangent what I mentioned, and this is the normal. You can also consider another plane which is perpendicular to the tangent plane. Actually, the name of the tangent plane is osculating plane, as I mentioned, and this is normal as I have shown here. And this red colored plane is considered as the perpendicular plane of the osculating plane, and this plane is called normal plane. We will come to that. And so, the curvature at that point is shown here by this quantity. Now, it is basically radius of circle is giving you inverse of the curvature. So, center of that circle which forms at that point due to curvature has been shown, and it should lie on the normal, and this plane is a normal plane. As I was mentioning, that normal plane is the perpendicular plane to the osculating plane. So, you have these two planes. Now, you can have another plane also which is perpendicular to both of these planes, and that is called rectifying plane. So, these are the three planes which are defined with respect to a point P by considering the direction of tangent and also the osculating plane normal, and so normal of the curve at that point. So, the binormal is a direction which is perpendicular to normal and tangent of the curve. So, that is binormal. So, binormal lies in the rectifying plane and also in the normal plane. So, it is the intersection of normal and rectifying plane. So, you can see as if at every point you have defined a coordinate system. That means, you have three axes which are perpendicular, and it can define a local coordinate system. So, this is called the moving trihedron or Frenet frame. So, this particular configuration, and the relationships between the tangent and normals in the differential geometric operations, those can be expressed. Here all are unit vectors, and if you take the derivative of tangent, you will get the curvature, you will get the normal vector, unit normal vector, which is magnitude, which was magnitude not unit normal vector, it is a vector along the normal of the curve with the magnitude. Magnitude is the curvature. Similarly, if I take the derivative of the binormals, and then the vector what you get, once again it is along the normal of the curve, but its magnitude will be modified by a quantity called minus tau, which is called torsion of this curve, and the derivative of normal is related with the directions of tangent and binormal in a linear form. You can see that this is lying in the plane of rectifying plane, particularly this direction. So, it is some directions in the rectifying plane. So, that is expressed. So, these are the three I should say very fundamental relationships between the change of directions of tangent, binormal and normal with respect to its curvature and torsions of the curve. So, we discussed about the representation of parametric curve, and also we have discussed some concepts, several concepts on normal, osculating plane, normal plane, rectifying plane, normal, binormal, curvatures and torsions of the curve. So, let us now consider representation of surfaces, because range data, as you understand, mostly it is a surface data, and of course, a curve would lie on a surface, and also you can try to treat the surface in totality around a point. So, parametric surface representation, once again here you require two parameters. So, surface is a two dimensional entity. So, it is a mapping from a 2-dimensional real space to a 3-dimensional real space. Once again, the parameters may vary within certain finite ranges. So, you can consider mapping from a subset of real space to the 3-dimensional real space. And there a coordinate is surface coordinate is represented by the x, y, z coordinate, and each one is a function of these two parameters u and v. So, let us consider a curve which is lying on the surface, and at a particular point I can get a directions. We have shown here, say suppose this is a point P, and a curve is if I consider it is varying over u only, whereas v is kept constant. This is how a curve could be defined when your one parameter is varying, other is constant. Then it gets a single parametric description of points, and then it becomes a curve on the surface. And you consider another curve on the same point, passing through that same point, where it varies over v and u is constant. So, you get for that you get another say tangent directions. So, now the normal at the surface point. So, actually x u and x b, these are all tangents, and there is a plane touching that surface at that point. In that plane, all these tangential directions are lying, all these tangents are lying. So, that is called tangent plane, and surface and the normal to that tangent plane is the normal at that point, which is called surface normal. So, if I denote it by the vector n in that case, and you can see that how surface normal could be computed using these two tangents, because it is perpendicular to these vectors x u and x b. So, you can take simply cross product of them, then you can get the directions of the normal, and as a vector if you normalize it, you get the unit vector along this normal. So, that is how the normal at this point computed, and that would be giving you the unit normal vector. So, these are the things we discussed, and then how we can represent a curve on the surface in the parameterized forms. I have mentioned that if you make one of the parameter constant and the other parameter varying, you get a curve, but in general what we can consider, even the parameter u and v is also described as a function of a single parameter. So, let us consider another variable t, which is again mapping the values from an interval of real space to the 2-dimensional real space, whose value which are actually coordinate, which are the values given by the combinations of u and v. So, this curve beta t equals u t v t, that itself will give you a parametric curve on the surface, because using these values of u and v for a particular t, you can get a curve on the surface. That is how you can represent any general curve on the surface. You need not keep one of the parameter u as constant, the other varying. You can vary both the parameters, but there is a relationship in them, there is a functional relationships in that variation, and that functional relationship is denoted by this variable function beta t, and which is denoting that parametric curve. So, if I expand them, we can see that corresponding to beta t, we get a curve on a surface whose x, y, z coordinates are given in this fashion. So, this is how it is given. So, tangent vector to this curve beta t, it is given in this form with this representation. It is familiar differential operations. You first get derivative of the function x with respect to u, partial derivative, and then you get the derivative of u with respect to t. Similarly, you get derivative of x with respect to v, and then again you get the derivative with respect to vt. So, each one will give you a vector. So, you can see x u is also a vector, x v is also a vector, whereas u prime t and v prime t you will get you will get a single scalar value, because ut is a function. So, you will get a function. So, it is a weighted combination of these two vectors that would give you the tangent. So, what I meant here, that if I perform the differentiation of this function and take some value t naught, that is a scalar quantity. So, but x u is a vector and x b is a vector. When you are performing partial derivative, you are getting x prime u v, y prime x u u v, y u u v and z u u v for x u. So, in this way you are getting vectors. So, you are getting the resultant of these two vectors x u and x b, that is giving you the tangent over that parametric curve. So, these are some of the key concepts of differential geometry characterizing the surfaces related to the gradient and curvatures. So, the first fundamental form, it relates the change of magnitudes, or it relates to the gradient directions at the surface point, and the magnitude of that magnitude of the tangent or changes in that surface point in the gradients. So, this is the bilinear form that associates two vectors in the tangent plane in the form of dot product. So, the definition of first fundamental form is that in the tangent plane, if I consider two vectors u and v, and if you take the dot product, that would give you the corresponding first fundamental form. So, with respect to a curve, parametric curve beta t, then this could be expressed as the dot product of t dot t, that is tangential directions, or this is a tangent. Actually, this t is a parameter, but this is tangent. So, you take the dot product of these two tangents, as we have discussed how tangents could be computed. So, we are expanding these two tangents. So, you get this particular quantity. So, this quantity is related to the first fundamental form. So, where you note that these parameters of capital E, capital F and capital G, which characterizes the first fundamental form, they are expressed as dot products of the corresponding partial derivatives of the functions in this. I mean, partial derivatives of the of the surface point with respect to u. So, this is just to expand. So, x u is nothing but you have say x u v, and this you are representing as say x u v, y u v and z u v. So, if I take the partial derivative of all these functions, and at a given u and v, you get a vector. So, that is how the x u is a vector. So, this is a vector, this is also. So, you take the magnitude of that vector, that is e. Similarly, you compute x b. So, you are computing x u as a vector, and similarly you compute x b as a vector from here, and you take the respective dot products and you get these solutions. So, the interpretation of first fundamental form, that it is the magnitude of the tangent vector. The other concept which is used in characterizing surface points and the surface geometry, local surface geometry, that is second fundamental form, and in the second fundamental form it is related to the curvatures. Let us see the definition. So, as we have already discussed, we can see that we have defined the normal as the cross product as the normal to the tangential plane, and which could be derived by taking the tangents at a point along two curves, which could be x u and x v. That means, where varying only u and taking v constant, and varying only v taking u constant, and you can compute normal. So, in this particular diagram, it is shown that if I have a curve where it is varying along v, and if I consider with its variations how the normal is changing its directions. So, that itself, that change of normal, that is expressed by a vector d and v, that is shown here. And let us continue. So, the definition of second fundamental form is that it is the dot product of two vectors u and v, not dot product. So, it is a function of two directions, tangential directions u and v at this point, which is given in this term u vector and d and v vector. So, as you vary v, so this term is d and v. So, it is a tangent, it is basically dot product of tangent with respect to d and v. So, tangent is another curve, this is not the same direction. So, we already know t dot n is 0. So, if I take if I take u and v both as t, then actually we get these relationships. So, since tangent is perpendicular to normal, so t dot n is 0, and then we take the derivative with respect to v. So, we get dt dv n and t dn v, that is equal to 0. So, this is the derivative. So, from there we are deriving with respect to v, and so we have already seen that if I take the derivative of tangent, you will get the normal of the curve at that point. I mean, a vector along the normal of the curve whose magnitude would be the curvature at that point. So, you get this quantity here. So, this is coming from this, and this is the actually second fundamental form. So, from there I can derive that second fundamental form could be expressed as k, it is a curvature, and this is the angle. So, this is cosine of that angle, because it is a dot product of two vectors, normal, and these are all unit vectors. So, this is the angle between these two, that would give you the corresponding cos phi. So, this is how the second fundamental form is interpreted, and you should note that they are unit vector. So, angle between curve normal and surface normal, that is the interpretation. And if you have a normal section, that means when your curve is lying on the normal plane itself, then this angle becomes 0. Okay. So, it is something like this, that you have a normal section. So, your curve is lying like this in this intersection here, normal plane. So, your normal section, so this is a tangential plane. So, the direction of normal and surface normal both are I mean either 0 or 180 degree, whatever, depending upon the topology of that point, but the dot product would be 0, and you get sorry, not dot product would be either 1 or minus 1. So, in this way you can get the corresponding surface curve, and this is called normal curvature. So, with this let me stop here for this lecture. We will continue our discussion on differential geometry as and its in the context of analyzing range image and its applications for characterizing surfaces in our subsequent lectures. Thank you very much for your attention.